Okay, guys, we're going to run through two examples of doing chi-squares with genetics. The formula is still the same. Really, the big thing here is how to find your expected when you're going through and doing these. You did this, whether you realized it or not, when we were doing the problems the other day, and you had that problem that asked about the 100 birds and how many of those 100 birds would have the different kinds of feathers, and you had to apply your 3/4 ratio to 100s. You do the same thing when you're trying to find expected for genetics problems. You apply those ratios you get from your Punnett square, and then you determine how many out of the number that you observed. So we're going to walk through two examples of these, okay, that y'all can follow along with while I go through them on here. So the first one here, we've got homozygous green peas were crossed with homozygous yellow peas. All the offspring were phenotypically yellow. A test cross was performed with one of the offspring from the F1. So using Y as the symbol for pea color, what are the genotypes of the parents used in this cross? Okay, well, I know I have one parent that was homozygous green, and green is actually going to be lowercase y. Okay, and I have another parent that is homozygous yellow, and that parent is going to be uppercase Y. And I know this because it told me that all of my offspring looked yellow. So if they all looked yellow, that tells me that yellow was dominant. Okay, so now it tells me here in the F2 generation that consisted of 20 offspring, predict how many will be green and how many will be yellow. Well, so my parent generation, so this genotype right here, this is my P. The offspring of them is my F1. So the offspring of this particular cross, which would all be big Y, little y, right? That's my F1 generation. So now I'm finding my F2 generation. Well, my F2 generation is a cross of two F1s. So to find my F2 generation, I'm going to have this particular cross right here. And like we worked on the other day, you need to have this cross memorized. You should not have to do it all the time. Okay, but we'll do it here. So I've got this particular cross, so I end up with homozygous dominant, heterozygous, and homozygous recessive. Okay, so I end up with, I'm talking about phenotypes here. It wants to know how many will be green and how many will be yellow. Well, I know my ratio here is 3 of them will be yellow, right? And 1 of them will be green. So again, I know I have that 3/4 or 25%, okay, or 75%. And then for green ones, I have 1/4 or 25%. So I need to apply that to 20. Okay, so if I'm applying that to 20, then I'm going to have 0.75 for my yellow ones times 20, okay, or 3/4 of 20. I need to do some erasing to make some room for this. So apparently erasing and I are not going to happen right now. So we're just going to cram it in there. So I would take to find my green ones, I would take my 0.25 times 20, right? So, or I'd find my 1/4 of them. So 1/4 of 20 would be 5, right? So I have 5, that will be green. And then to find yellow ones, I'd have my 0.75 times 20, because I'm applying this ratio that I got here in my Punnett square. So I'd have 15 of them would be yellow. Okay, I'll keep in mind that I'm having trouble erasing and make it fit better on the other ones. So if I'm looking at part C here, if the offspring consisted of 8 yellow peas and 12 green peas, would this be statistically different from my prediction? Use the chi-square to do it. Show my work. What's my best explanation for the differences? Okay, so I set my chi-square up in the same way, right? I observed and I expected. So I observed yellow and I observed green. So I observed, I'm a yellow, 8 yellow. I observed 12 green. I expected, and I calculated that up here in section B, right? I used my Punnett square and I calculated that. So I expected to see 15 yellow ones, and I expected to see 5 green ones. So now I just plug that in, right? O minus E squared, and then divide that answer by E. Okay, so I just plug that in. So I get 8 minus 15 squared is 7 squared, so 49. Same here, 12 minus 5 squared. 12 minus 5 is 7, squared is 49. So then I divide that by E, and I'm going to get 49 divided by 15, which is 3.27. Okay, and then I have 49 divided by 5, which is 9.8. For my actual chi-square value, I need to sum those up. So 9.8 plus 3.27 gives me 13.07. I still need to do all of my other values, right? I still need my p-value, which is always 0.05. I need my degrees of freedom, right? My degrees of freedom in this case would be 2 minus 1, so 1. I need my critical value, right? And I get that from my chart. Y'all can grab your formula charts to be able to have access to that chi-square table. So my degrees of freedom in this case are 1. My p-value is 0.05. So my critical value is 3.84. Okay, I don't have any more room to write, but you need to be sure you're writing the rest of your analysis. Remember, I need to compare my chi-square value to my critical value. My chi-square value in this case is greater than my critical value. That tells me that the results are statistically significant. Therefore, in this case, it's asking my best explanation. So I would have failed. I would have rejected my null hypothesis. In genetics, your null hypothesis is that they follow traditional Mendelian genetics. So my best explanation for the difference between the two is that this does not follow that traditional Mendelian genetic inheritance. There are other things that are factored into the color than just one gene. Okay, and so that would be my analysis there. Again, my chi-square value is greater than my critical value. Therefore, I would reject that null hypothesis. So my explanation would be that these do not follow traditional Mendelian genetics. Okay, so let's look down at part D here then. There are 200 offspring, and they consisted of 80 yellow peas and 120 green peas. Would this be statistically different from my prediction? I have to do the chi-square value again. I cannot look at this and say, oh, 12 with a 0, 8 with a 0, it's the same. Okay, because right now I have a much bigger sample size. So I need to apply my expected and everything to that as well. Right, so I have my observed and my expected. Well, I observed for yellow ones, I observed 80. For green ones, I observed 120. For expected, I expected, again, back up here to part B, I expected 3/4 or 75% of my offspring to look yellow, to look dominant. So 3/4 or 75% of 200 is 150. Okay, I expected 1/4 of my peas to look green, or 25% of them. Well, that would be 50. So now I do my observed minus expected squared. Okay, and so I get 70 squared, right? 80 minus 150 is 70. So 70 times 70 gives me 4,900. Okay, 120 minus 50 again is 70. So again, I'm at 4,900. Divide that by my expected, right? Observe minus expected squared over E. So 4,900 divided by 150 gives me 32.67. I probably already know what's going to go on now, right? 4,900 divided by 50 gives me 98. My chi-square value is 98 plus 32.67. So 98 plus 32.67 is 130.67. Still got to write all this. P-value is 0.05. Degrees of freedom equal 1. Critical value, again, using my chart to find my critical value, still have 1 degree of freedom, still have p-value of 0.05. So I'm at 3.84, right? My chi-square value is greater than my critical value. Therefore, I reject my null hypothesis. So in genetics, I would say that these do not follow traditional Mendelian genetics. Okay? All right, let's look at the second example on the back. Okay, let's go through this one real quick. Ignore the big blue line through the middle of the words. I can't get it to erase, and it's almost 9 o'clock, and I'm at school getting this ready for you. So just ignore it. All right, so let's look at this. So I've got in certain strains of corn, the phenotype can be yellow or purple. Texture can be plump or smooth, or it can be wrinkled. I've crossed a homozygous purple and a wrinkled strain of corn, crossed with a homozygous yellow and a smooth strain of corn. The offspring were all smooth and purple. The F1 offspring were crossed with one another, and the phenotypes of the kernels from several ears of corn were counted and recorded in the data below. So my F1 offspring, okay, it told me that my parent offspring, when I crossed them, I got all kernels that were smooth and purple. So that tells me that purple is dominant. So my F1 offspring is heterozygous, big P, little p, and smooth is dominant. So big S, little s. So that's my F1 generation, right? I crossed 2 of those to get my F2 generation. So this generation right here, this F2 generation, is a result of a dihybrid heterozygous cross. Okay, so that's the result of that. It wants to know the null hypothesis of this investigation. Okay, well, your null hypothesis, again, in genetics, is that they would follow Mendelian genetic patterns. And for this particular cross, a dihybrid heterozygous cross, it would follow the typical Mendelian genetic pattern of that 9:3:3:1 genotypic ratio. This is another thing you need to just get memorized. You should not have to calculate this every single time. As a reminder about what phenotypic ratio is in a dihybrid, remember they look dominant for both traits. So in this case, I've got 9 of them when I do my cross, whether it's the 2 monohybrid boxes or the 1 giant dihybrid. 9 of them will look dominant, so they will look purple and they will look smooth. Okay, my second number is they look dominant and then they look recessive. So I'd have 3 of them that look purple because that's dominant, but they look wrinkled because that's recessive. My second 3 is that they look recessive, then they look dominant. So I'd have 3 of them that look yellow but look smooth. And then my last one is going to be recessive. So in this case, I'd have 1 that would look yellow and it would look wrinkled. And if I add all these up, they add up to 16. Okay, all my possibilities. So I'm going to have to take this ratio and I'm going to need to apply it to get my expected. So if I'm doing a chi-square analysis to see if this supports my null hypothesis that they follow Mendelian patterns, okay, I'm going to need to take my observed. Okay, and I'm going to need, so I've got purple and smooth. I've got yellow and smooth. I've got purple and wrinkled, and then I have purple and, I have yellow and wrinkled. Okay, so what I observed is 375 purple and smooth, 133 purple and wrinkled. So I'm on yellow and smooth, I have 118, and I observed 47 that are yellow and wrinkled. So these are what I observed. So I observed a total, it didn't give me that in my information, so I need to add these up. So 375 plus 118 plus 133 plus 47. So I observed a total of 673 kernels. Okay, now I need to take this ratio that I got back here in part A, or that I got from my cross. My ratio comes from my traditional cross right here for my F2 generation. To find my F2 generation, what would my outcome have been? So it should have been 9 out of 16 look dominant, right? That's my ratio. 9 out of 16 look dominant for both, which translates to 0.56 56.25. So now if I apply that to my total, right, because that's 56.25%. So I've got 0.5625 times my total, which is 673. So 673 times 0.5625. I should have seen, so my expected, I should have seen 378.56. So 379 kernels that looked dominant. So my next number is dominant recessive, and I have 3 out of 16. 3 out of 16 turns into 0.1875, or 18.75%. Apply that to my total. So 0.1875 times 673 gives me 126 kernels. Should have looked dominant recessive. Well, recessive dominant is the same thing. So I've got, for recessive dominant, I've got 3 out of 16, or 18.75%. So again, applying that to my total of 673, I'd have 126. Should have looked recessive dominant. And then for recessive, I have 1 out of 16, which turns into 0.0625, okay, or 6.25%. So when I apply that to my total, 0.0625 times 673, I get 42. And I can double check my work by adding them up and making sure that they equal 673. So I have 42 plus 126 plus 126 plus 379. So I still have a total of 673. So now I just plug this into the calculator, right? Observe minus expected squared over observe minus expected squared divided by E. So in my purple smooth ones, I have 375 minus 379. So I have 4 squared, which is 16. 16 divided by 379 gives me 0.042. Let's take it out 3 decimal places. Okay, so for my next line, 118 minus 126. 8 squared is 64. 64 divided by 126 gives me 0.508. 133 minus 126 squared gives me 49. So 7 squared gives me 49 divided by 126 again. I'm at 0.389. And then 47 minus 42 is 5. Squared is 25. 25 divided by 42 gives me 0.595. I need to add all those up, right, to get my chi-square value. So 0.042 plus 0.508 plus 0.389 plus 0.595. I can barely read that. Okay, gives me a total of 1.534. P-value is the same as always, right? P is 0.05. Degrees of freedom in this case equal 3, right? 4 minus 1. My critical value, I'm going to read from my chart. So this time when I'm looking at my chart, I'm looking at the degrees of freedom column of 3 and my p-value of 0.05. So now I'm at my critical value is 7.82. So this time I would accept, right? My critical value is greater than my chi-square, or my chi-square value is less than my critical value. So I accept my null hypothesis that this follows Mendelian genetics problems, and any differences are just due to chance, possibly due to sample size. Okay? So those are 2 examples of how to get expected with genetics problems. So you can work through your practice work and go ahead and take care of those.